Hi, good afternoon, everyone, and welcome to our webinar this afternoon. We're delighted to have so many who have taken time to attend. My name is John McLaughlin. I'm a senior software engineer in TSSG, and as such, I've worked on the piSCES project, setting up a platform and helping with data analytics. Joining us today on the webinar are project partners from the Port of Milford Haven, Bord Iascaigh Mhara, the Atlantic Dawn Group, and Cardiff University. So each partner will give an overview of the different perspectives on the piSCES system as it affects them. So in areas such as system simulation and fish processing in Ireland. And we'll introduce you to the trial sites in both Wales and Ireland. Before we begin, the principal investigator, Sean Lyons, is also the project coordinator, will give a brief introduction into the piSCES project to give you all a brief understanding and context on the trial sites and the piSCES platform. But before I hand over to Sean, I'll just do a little bit of housekeeping. So the webinar will be recorded, and we will circulate this to the attendees next week. Also, if you have any questions, there's a Q&A button just down at the bottom of your screens. So if you have any questions, you can pop them in there, and we'll have a Q&A session after the presentations. And we'll attempt to answer as many questions as we possibly can. So with that, I will hand you over to Sean, who, as I say, will give an overview of the project.
Thanks, John. I'll just share my screen and hopefully you'll be able to see it. Can you see that?
Yeah, I can see it, yeah.
Great, okay. Okay, thanks, John. Yeah, so look, I'm just going to give a very, very quick brief overview of what the project does, so as it'll put some context for the speakers that are coming. And then at the end, I'll go into a lot more detail on the platform that we've built to enable this. So piSCES it's an Ireland Wales Interreg funded program. And there's 4 partners, ourselves, TSSG and WIT in Waterford, the Cardiff University, the Port of Milford Haven, and Bord Iascaigh Mhara. So as John said, each will give a brief overview of our work here. So very quickly, this is just a graphic to explain what piSCES does. So we're very much working with large marine type sites such as fish processors that have a large energy load and a degree of flexibility to that load. And what we mean by flexibility is that you have the potential to ramp it up or ramp it down. So, you know, we've focused very much on thermal loads where you've got like cold storage or ice making. And basically, in the case of a cold store, you can make it colder or you've got a temperature band that you've got to keep it within. So you can make it colder at certain times and at certain times and maybe let that temperature rise slightly. So why would you do that? Basically, on the electricity markets, the price of energy changes every half hour on the wholesale markets, which you can trade on. And you can trade on that on a day-ahead market, so you know what the price of energy is going to be tomorrow, okay? And also, piSCES is focused on integrating renewable energy at the site of those loads. So it could be wind or it could be rooftop solar. And again, we built a prediction system to give us a view as to what the local energy that we own is going to produce in the next 24 or 36 hours. And then we've done, with those prediction models, we've developed optimization algorithms to ramp up and down those flexible loads based on time of use tariffs on the electricity market and available renewable energy. And also, if you have a battery, you can ramp that up and down as well. So that's just to give a very quick overview of and provide some context for what the speakers are going to come up with now. So I'll be back to you later with a more in-depth of the platform. Okay. So I believe, John, the next item on the agenda is the welcome from the minister. Is that correct?
That's correct, Sean. Yes. So we were very pleased to have the Welsh Minister for Environment, Energy and Rural Affairs, Ms. Lesley Griffiths, officially open the webinar this afternoon. Unfortunately, she wasn't able to attend live, but she has sent us this brief message. So, Sean, I think you have the video for that.
Okay, can you see that?
Yeah,
great.
That's good.
Okay, let's play it now.
Pnawn good afternoon. I'm delighted to open today's event, which celebrates the work and the achievements of the piSCES cross-border project. The project, backed by over €1.8 million of EU funding from the Ireland Wales Cooperation Programme, aims to support the fisheries industry across our shared waters by developing a new smart grid electricity network to help reduce energy costs, reduce carbon footprint, and improve the quality and security of energy supply. The fisheries industry is an important part of the food and drink sector and wider economy, sustaining livelihoods and communities across our coasts. It is crucial we ensure the industry has a viable future, especially given the recent challenges it has faced in light of the COVID-19 pandemic, as well as any potential challenges at the end of the transition period. Today you'll hear in a lot more detail what piSCES has achieved. I'm delighted to learn that technology implemented at a number of processing sites has resulted in significant savings and improved sustainability, helping them play a central role in the clean energy transition. piSCES have combined the skill sets of TSSG and Cardiff University, two leading research and development institutions in this space, to define and develop new technologies to suit the specific requirements of fish processing sites. Plus, with BIM and Milford Haven Port Authority engaging with and including processing sites in the partnership, they've ensured specific requirements have been catered for, making results which are tangible and more market specific. In recent years, Wales has raised its ambition and we've delivered real changes, all of which go some way in helping us to respond to the ongoing climate crisis. However, we still have some distance to go in reaching our more long-term climate and environmental goals. This month marks 5 years since the signing of the International Paris Agreement, and as we start the countdown towards the UN's Climate Change Conference, COP26, in Glasgow next November, we want to show the world we are a globally responsible nation and ready to play our part. Collaborative cross-border projects such as piSCES, the Irish Sea Portal Pilot Project and Bluefish already form an important part of this work. By looking at the challenges of climate change and decarbonisation in an imaginative and creative way, by engaging with coastal communities, businesses such as fishing, shellfish and aquaculture industry, and by sharing best practice and expert knowledge. We also want to ensure the shared resource of the Irish Sea continues to be managed in a sustainable way, allowing for industry growth and protecting it for future generations. We will look to continue a cross-border strategic approach with our Irish counterparts, encouraging knowledge transfer, engaging with coastal communities, and closely working with industry to inform blue growth. Ireland is not only our closest EU neighbour post-Brexit, but also our natural partner, both economically and culturally, and cross-border work like this will continue to be an essential part of our international strategy moving forward. I would like to congratulate TSSG, Cardiff University, Milford Haven Port Authority and BIM for the successful delivery of the piSCES project. I hope you all enjoyed the rest of this event. Diolch.
Thank you. That was Lesley Griffiths, Welsh Minister for Environment, Energy and Rural Affairs, and thanks again to her for taking the time to give us that message. Next up, we have Dr. Johan Petri of the School of Engineering from Cardiff University, and Johan is going to give us a presentation on system simulation. So I'll hand you over to you, Johan.
Thanks, John. Thanks for this. Here's my screen. Can you see the screen?
Yeah. I see that, Leon.
Yeah, thank you everyone for attending. It's a pleasure to be presenting our work that we've done as part of the piSCES project, in particular looking at a system simulation. So my name is John Petri. I'm a lecturer in School of Engineering at Cardiff University. Today I'll briefly explain the research-driven approach that we've adopted as part of piSCES with a view to inform technical implementations and pilot implementation. So we leverage on this concept of a port fish industrial site as a complex systems where there's a dynamics in terms of energy consumption and production, an increased number of variables and associated constraints, multiple buildings, spaces, and appliances. Also, nevertheless, we consider human factors involved, which can significantly influence the overall process. So the diagram is presenting a broad literature review that we undertaken from different scientific sources at a range of publications, resulting in a 400 plus publications, from which 54 have been evaluated and lesson learned, extracted, and really solutions reviewed. And the objective was to look into ways of optimizing energy networks with significant impact on the CO2 emissions by utilizing a simulation, prediction, and optimization capability for energy and carbon reduction. And really our approach was a holistic approach, looking at the building level, also at the site level, and the appliance level. And on the right side, you can see a diagram that reflects the methodology that we've adopted for developing this science-supported methodology, really from the thermal model definitions, a cost simulator, environment, and what-if scenarios, and different control algorithms that we've implemented. So from a perspective of a site and a building, we have different appliances, and we managed to collect different requirements as part of our requirements elicitation process, where questionnaires and interviews were utilized as a method to extract knowledge and information about the pilot project. And in here, some preliminary tests that we've implemented with a view to look at different operating schedules and their associated impact on energy consumption, while taking into account constraints such as power rating, minimum running time, interruption of appliance, and required user frequency for different appliances that we utilized. On a cluster level, on a site level, we've looked really to find ways of achieving impact with the observation that impacts have different granularity when discussing an appliance, for instance, or building, and a site level where decisions can have different value in terms of costs and energy consumption. In here, we present the calibration that we've also added to our simulation capability, where the simulation was really an energy model developed using Energy Plus and Simulink. And you can see that our simulation capability has really been a digital replication of the existing phenomenon. So the actual energy consumption and the simulated energy consumption really go on a one-to-one correlation, which was extremely useful, because after we have a digital replica, we can test different scenarios which in practice we couldn't test due to restrictions that exist in the sites. In here, we report a renewable integration and battery capability that we've also developed through the simulation capability that we've developed, where different type of battery performances have been tested with different input parameters such as capacity, voltage, type, and hours, with a view to develop this smart microgrid model that takes into consideration production units, but also consumption units that may exist at the level of a fishery site. Nevertheless, to integrate all these elements which have a certain complexity in the modeling, we utilized ontologies as a mean to represent knowledge for different appliances and buildings, and to determine possible impacts and correlations between different variables also and components that may exist in a site. Really with the objective to have a quite robust and flexible simulation capability that can inform the development of a prediction and also optimization in sites. So for instance, our simulation capability framework can take as inputs weather factors, production factors, consumption factors, price factors, demand and time factors, with a view to maximize or minimize certain objectives such as production, consumption, and CO2 emissions, while instrumenting different values for the schedules and the set points at the level of appliance. And such simulation capability would give decision factors ability to take informed decisions when to store, use, sell, buy, or schedule energy based on different events or constraints that may appear. A simulation-informed prediction framework has been also developed where different input data such as season, capacity, predicted temperature, power have been utilized with a view to enable forecasting of future scenarios, where the input layer was primarily modeled around variables such as power, temperature, set point, capacity, and season, and the output layer, the result that provides future projections, is around temperature and power. Really, the objective was to have a workflow supported by science and evidences aggregated from the literature, but also from the very detailed requirements elicitation phase that we conducted in the trial sites, to understand what can happen in future in terms of energy consumption and demand, but more importantly, to enable decision-making and actionable insights at the port level. In this context of informing practice, informing our industrial partners, and also provide a high order of information for communities and stakeholders. And in here, we explain how different prediction models have been tested. They provide different efficiencies, and we've chosen the best really prediction, which is an artificial neural network that was resulted after model benchmarking and gives a forecasting of energy and temperature for 30 minutes and 1 hour ahead forecasting. Now, an element that is also present and was the result of our work is exploring this transition to sharing economies and energy communities. And our simulation capability was scalable to a community level and enabled methods for digitalizing ports in terms of processes and resources, and also a higher grade of scalability to cover more efficient cost scenarios, where objective one was consumers to have the ability to increasingly generating their own energy and monetize the energy by trading in a market of options among producers and consumers. And I will very quickly report on, for instance, this idea of peer-to-peer clusters that we've started to develop based on a lower granularity. For instance, we started with the trial projects that were present in the project, but we expanded to a community layer where we managed to test around 1,000 participants, communities formed of producers, energy producers, and consumers that are organized in clusters. We considered in-cluster and in-federation energy exchanges, and you can see results that have been disseminated in IEEE journals, where different types of energy with different type of demand can interact, and these are reported in here. You can see the impact of different levels of energy demand, a different simulation cycle. I will convey the conclusions, saying that the simulation container and the simulation capability that we developed was meant to deliver a real-time user-oriented decision support by also enabling adaptive appliance actuation based on generation and demand, cost analysis and optimization forecasting, with objectives in relation to environmental impact and modeling, where prediction was directly correlated with reaction triggers at the appliance level and remote actuation. Really, our system simulation capability can inform autonomous coordination for the entire fish processing workflow, and providing advices when to store, when to send energy, and when to use energy, all being part of a greater challenge that we contributed to, developing digital twinning strategies for fishery ports, where simulation, prediction, and optimization can actually support different actionable insights at the port level. This was my presentation. Thank you very much.
So next up, we have Martina O'Brien, a Green Programme Coordinator from Bordell Kivara, who is going to give us a presentation on fish processing in Ireland and piSCES. So hand over to Martina.
Can you see that there?
Yeah, that's good, Martina. Yeah.
Great, thanks. Hi, everyone. Thanks, John, and thanks for the opportunity to speak here today. So, as John said, I'm from the Irish Seafood Board, Bordell Kivara. And as a semi-state organisation, it's our job to provide support and assistance with the development of the seafood industry, and that's across fisheries, aquaculture, processing, and retail. So we primarily provide strategic and business support, but also technical support to the industry. So today I'm just going to talk to you, give you a brief overview of the Irish seafood industry, the importance of sustainable development in driving the industry forward. I'm going to talk to you about Origin Green, which is our national sustainability programme for food and drink companies. I'm also going to talk about the BIM Green Seafood Business Programme and how it provides tailored supports to seafood processors and its link with this piSCES project. So, as an island nation, the sea and the seafood industry are inextricably linked with our culture and heritage. But the seafood industry as a whole forms a significant and important part of our national economy. In 2019, it contributed 1.2 billion in GDP and provided employment to over 16,000 people. As a subsector of the seafood processing, seafood processing contributes most significantly to the industry overall. And in 2019, there were 164 seafood processing companies operating throughout Ireland. These companies generated over 700 million to the economy. They provided 4,076 jobs, and port towns the port towns of Castledownbere and Killybegs, which provided trial sites for this project, were two of the biggest fishing ports based on the value of their landings. So the demand for seafood remains strong in 2019 and is continuing to increase. And despite the challenges of Brexit and the emerging COVID-19 pandemic in 2019, demand for Irish seafood remains strong and continue to grow in line with global demand for high quality seafood. So generally, the increasing demand for seafood is a trend that will likely continue. As we know, by 2050, there's going to be 9.7 billion people on the planet, and the sustainable provision of food is going to play a key role in meeting that demand. But it's going to play out, seafood obviously being a protein-rich food source, and nutritious is going to play a key role. But this expansion of the seafood industry is going to play out in the context of climate change, and in the context of an increasing demand on finite resources, and this will the rapid growth of our global population will put further pressure on resources like energy and water, and it's likely that the costs of these will also increase. And we're already seeing that play out as non-domestic user tariffs are increasing in Ireland. So the question really is, how do we develop and expand the industry in a sustainable and cost-effective way? And how do we square that circle? Globally, food systems are responsible for 24% of greenhouse gas emissions. Agricultural systems play a significant role in that, but seafood processing has also been identified as an energy-intensive industry. This is particularly due to the fact, as we've heard, the nature of the industry. Cooling and freezing are the biggest consumers of electricity. Cooling systems also produce gases, refrigerant gases, which are contributing to global warming. And it's not surprising that energy costs represent the largest overhead in the fishing industry. Through our National Climate Action Plan, Ireland has committed to a 7% reduction in greenhouse gas emissions, and the plan focuses on our primary industries, agriculture, forestry and fisheries, and the actions that they're going to take to help the country move forward on our journey to a net zero economy. And this is in line with EU legislation pushing for climate neutrality by 2050. It's not just this top-down push from government and legislation. Sustainability is a key factor in consumer choice, and consumers are increasingly striving to live responsibly. They purchase goods that reflect their values, and they expect transparency from suppliers to help them make these decisions. So as a primary industry, the importance of acting on sustainability is even more significant in the seafood industry, as our supply of raw materials like fish and aquaculture stock rely upon the health and functioning of ecosystems, and there's a need there, a necessity for the industry to act collectively to address climate change and greenhouse gases, and to safeguard the future of our industry. So readying the seafood industry is a challenge, but it's part of our job in BIM to work with and to listen to the industry and to look ahead to see what's coming down the line. So in response to this, and in conjunction with BIM, are working to support companies to engage in a sustainability program called Origin Green. And this is a national program which aims to embed sustainability into the DNA of the Irish food production sector. The programme offers a structured approach to tackling sustainability, and it helps to define the types of areas that companies could tackle. So you can see here raw material sourcing is a key target area, manufacturing processes, and social sustainability. And they're the 3 target areas, and within them different targets can be addressed. So things like supplier certification, primary producer, sustainability initiatives, packaging, and within manufacturing processes, energy and emissions are a key target and a mandatory target for all companies. So this programme allows companies to define their baseline usage to determine that in the first year of the programme, and then to set targets under all of those different target areas and different target headings. So this is really where the piSCES project kind of fits in terms of the companies that participated in this piSCES programme. They're able to then report back on the work that they've done and the savings that they've made through this programme. So this is just the template that's used, and you can see the detail that's required on reporting back and measuring progress for energy under the energy target. So where the Origin Green plan provides a structured plan for companies to decide how they want to act. The Green Seafood Business Programme is a BIM programme that was initiated in 2012, and it provides support to putting into action those plans. So the programme essentially involves an on-site visit. There's quite a diversity of seafood processing facilities in Ireland. Some are big, some are small, and they operate with different species. So having an on-site visit where resource efficiency can be assessed and a plan can be made is an essential part of the programme. And the programme also provides ongoing assistance and follow-up meetings and reviews. So in a nutshell, this is just an overview of the types of resources that the programme looks at and where kind of quick wins can be made. So things like conducting detecting water leaks on site have allowed companies to save €20,000 per year in water charges. And this is again where the piSCES project fits in, where it can look at how to optimise energy usage on site. So things like looking at cold stores and kind of basic things like even the door seals on cold stores and things like that. So just moved on. So the most important thing about the Green Seafood Business Programme is that it's not a static programme, it's dynamic. And again, this is where the piSCES project fits in, is that it contributes substantially to how the programme will operate with companies going forward. So now that we know that the benefits of these types of projects and the novel technology that's involved and the way that the industry is heading, the energy industry is heading, and the paradigm shift from decentralization, from a centralized system to a decentralized system, where companies can really take ownership of their energy use and potential production through renewable energies. I think this is where there's real value in Irish companies participating in programs like this, so that it can feed back into these kind of on the ground programs. So two companies that participated in the trial, acted as trial sites in Ireland, were the Atlantic Dawn Group, so Arctic and Polar Ice, and Castletown Bear Co-op. And it's companies like these participating in programs, projects like this, that really allows BIM and our industry as a whole to benefit. So I'm not going to go into detail here on the case study because that's going to be covered by Philip Kelly later, as he was involved he's from the Atlantic Dawn Group and was involved in the trial and the rollout of the trial. So I think just suffices to say that site savings were in the range of 15 to 18%. That's obviously a massive benefit, and other coal store efficiencies were achieved through participation in this. And just on behalf of BIM, I want to say a big thank you to the companies who participated in the project for giving their time to support its development, and because the benefits of it are going to be felt throughout the industry. So thank you very much. That's me.
Thank you very much, Martina. So next up we have Tam Bardell, who's Energy Development Manager for the Port of Milford Haven. And Tam will give us his perspective as a trial site in Wales on piSCES and energy clusters. So Tam, I'll hand over to you.
Can you see my screen all right, John?
Yeah, that's
brilliant, thanks. So Milford Haven was an implementation partner in the project, and we're Wales's biggest fishing port. So it was really great to be part of this project. So we had two implementation sites for piSCES. The first one was the Parkaway building, which is owned by the Port Authority, and it's where we make ice for our fisheries tenants. And the other one was Williams Marine, which is a fish processing tenant based in Milford Fish Docks. Also, I'm going to talk to you about the smart energy cluster, which we got set up in our fish docks, and give you a bit more context around that. But first of all, let's speak about Parkaway. So focusing in on the flake ice production in the Parkaway building, if we go back to 2018, when we first got involved with piSCES, we had energy monitoring equipment put into Parkaway building in 2017 to give us a really good indication of what was happening in the building in terms of energy consumption and generation. And this graph here is showing you the typical sort of pattern that we would operate the flake ice machine by. So we tend to put it on at 4 or 5 in the morning and then leave it running until we made enough ice to give to our tenants. You can see the little table there on the graph on the slide is showing that half of the ice roughly was made on a nighttime rate of 6.5 pence, and the other half was made on a daytime energy tariff rate of 12 pence. So the total cost to make that ice in that period was about £4.60. But of course, with our piSCES hat on, we started exploring the opportunity of running the machines differently. So if you go to the day before that ice was made, you can see that the solar system on the roof was generating a good amount of power. See where the red rectangle is, that shows about half of the ice could have been made over the peak of the day before. And if we'd have been making the ice at that time, it wouldn't have cost us anything. So that really woke us up to the opportunity. And then the other bit of that table is showing that if we'd have made half of the ice with the solar and the other half on a nighttime rate, the total cost to make that same amount of ice would have been £1.74. So £4.60 versus £1.74 shows a potential of 60 odd % saving on the ice order by using available solar PV and only off-peak tariffs. So piSCES really woke us up to the opportunity to save a significant amount of energy for our ice making. So fast forward to 2020, and what you're looking at on this chart is the green line is showing the energy footprint of the ice machines running, and the blue line is showing the solar generation. So Now we've got piSCES in operation on the site. You can see that piSCES has run one of the machines from 2 in the morning to 7 a.m. And that's when we go on the daytime rate. So it's run it on the cheap off-peak rate. And then it switched them 2 machines on then at 10 a.m. and run them till 2 in the afternoon. Now, if we hone in on that bit in the red rectangle, the table is showing the energy that's been used to make that amount of ice. So you can see that 45 kilowatt hours came from our solar system, and that costs us nothing. And then the other 20 kilowatt hours is on a day rate of 14.6p. So it's gone up since 2018. The amount we're paying for energy has gone up, and that's obviously an ongoing trend. So the total cost to make the ice there that's in that red rectangle was about £3. When you compare that to making that same amount of ice on a night rate, we've got a 60% saving there, so a significant saving. If you compare it to making that ice on a day rate, then it's a 70% saving. If we didn't have any solar on the roof, we'd be paying nearly £10 to make that ice during the day. And of course, this is a day in September. So if you compare it to a nice summer day in June, when the solar is really kicking out a lot of power, the savings increase to over 80%. So a really significant amount of savings. And what we did on this particular site is put in an internet connected switch so that piSCES, the software, can talk to the switch and switch the machines on and off. Our staff then can sit at their computer, place an ice order in advance, and allow piSCES to run the ice machines automatically and schedule them at the best time possible to save us the most amount of money. So we're seeing significant savings on our own building. Moving on then to Williams Marine. So as I say, Williams Marine is one of our fisheries tenants. They've got 3 freezers on the site. They're freezing bait for crab fishing over the winter. And then they have a chiller with lobster tanks and lots of pumps running, pushing air through these tanks to keep the live lobsters in good condition. We put energy monitoring onto the site and had a good look at the energy footprint of the different devices and really focused in on the freezers and the operation of the freezers, because that's really the big opportunity to schedule the running of the freezers differently to make better use of any renewable energy or off-peak tariffs. If you look at the chart on this slide, it's zooming in on one of the freezers and showing you the energy footprint of it. So you can see the compressors come on every 4 hours or so to keep the temperature about -11 degrees. So there's a good opportunity there to either reduce the temperature in the freezer or have a bigger band of temperatures that you're working within and operate the freezers differently. So if I go into the next slide, the green line on this slide is showing the total energy which is being pulled from the grid in a day in November this year. And you can see that there's quite a heavy base load on the site. There's quite a lot of power being consumed from the grid. The blue line is showing the solar generation on that day. Obviously not a massive amount of solar on a November day in Milford Haven. But what this is showing is that actually all of the solar is being used on the site when it's being generated. Now you can have a look at a summer's day, and I've done that, and you can see that obviously there's more solar being generated, but there's always this quite heavy base load because they've got a lot of pumps running, they've got freezers running. Most of the time the solar will be mopped up by the base load in the site. So the optimization here is to operate the freezers differently based on a half-hourly energy tariff, and that'll be the recommendation to Williams Marine. So going on to smart energy clustering. So the piSCES actually stands for Smart Cluster Energy System. The idea being that once you've cut the energy overheads for individual sites, as I've been describing, then you bring sites together into an energy cluster to allow them to sort of trade any spare energy that they're generating between them. So Williams Marine is a good example of that. You can see that they're using all of the solar on the site. If there was more solar available through a cluster model, then they'd be able to use that as well to offset their bills. So we started to investigate this in 2018 and looked around to see if anybody else was doing this sort of thing, and came across an example in North Wales and Bethesda, where the National Trust have a hydro on the side of the hill, and they were selling their power directly to homeowners in Bethesda. So we started speaking to them and to an energy charity called Energy Local, who'd implemented this way of being able to share energy through a contractual relationship with the energy supplier. So that really shakes things up, and we decided to go ahead with them, work with them to try and set up the UK's first commercial smart energy cluster. And that's what we've done. So this slide is showing we've got a site called the Dry Dock, which has a 50 kilowatt solar system on the roof. It doesn't have any load in the building. It's just an open-sided storage shed. So it's always just putting all of its power onto the grid. What we've managed to do is use that site, and as I say, through a contractual relationship, we're able to offset the bills on a number of sites within the local area through this equitable sharing method. And what that means is that within any half-hour period that the solar is generating, that power will be used to offset the bills on those sites equally if they're consuming power at the same time. So to explain a little bit more about the smart energy clustering, you've got the top left of the slide there, shows that, you know, what we've been doing is exporting to grid and being paid 5 pence per kilowatt hour to do that. So our income in 2019 from that was about £2,000. But of course, these other sites around and lots of our other properties are buying that same power back from the grid, but paying 14.5 pence per kilowatt hour. So there's got to be a better way than that, and that's what piSCES is all about. So what we've managed to set up in Milford Fish Docks is this smart energy cluster, whereby we're selling the solar power to ourselves. So you've got two income streams now. You're still exporting a little bit to the grid, so you can see we're estimated to export £340 a year to the grid. But we're now, the rest of that money that we would have been getting through the export tariff, we're getting back through solar sales to ourselves. So we're selling the power to ourselves at 5 pence per kilowatt hour and making an income, I suppose, or you could see it as a saving, whichever way you want to see it. But if you explain it as an income, then what we've also got, of course, is a cost saving, because we're not buying that power at 14.5 pence. We're buying it now at 5 pence. So we've got a significant saving. We've still got the same income from the solar system, exporting to grid and selling to ourselves, but we're also now saving a significant amount on our bill. So that's proven to be a really great way for us to save money on top of what, as I explained, with the flake ice operations. And it's something that we're looking to expand out across sites going forward. So we expect to expand what we've started in Milford Haven, and ideally, if we can, also set up another smart energy cluster across the water in Pembroke Port to save even more money. So thanks very much. That's my presentation.
Thanks for that, Tam. So next up, we have Phil Kelly, who's in the finance department for the Atlantic Dawn Group, who's going to give us a view of the trial site in Killybegs here in Ireland. And just before I hand over to Philip, I'll just draw your attention again to the Q&A box. So if you've any questions as we go along, just pop them in there and we will get to them at the end. Okay, I'll hand over to you now, Philip.
Okay, thank you, John. Can you see the screen okay there?
Not yet, no. Actually, Tam, do you have to stop sharing your screen, I wonder? I know you're not sharing.
I think I'd stop sharing.
Yeah.
Can you see my screen?
No. You should be good to go, Philip.
Okay. There we go. Can you see that now, John?
Yeah,
that's good.
Yeah.
Okay, so I'm Philip Kelly. I'm an accountant here at the Atlantic Dawn Group. I'm a member of the internal energy management team and also part of the company's Origin Green team. So just a little bit of the background to the company. We're one of Europe's largest producers of frozen pelagic fish. Our activities involve catching, processing and marketing frozen pelagic fish products. And our activities involve catching vessels, sea freezing vessels, and shore freezing factories, here in Killybegs. The company is, trying to bring up the slideshow there, the company is committed to sustainable fishing practices. We work closely with the MSC, the Marine Stewardship Council, which independently certifies a number of fisheries we're involved in as sustainable. And we're also a member of Origin Green, which is Ireland's food and drink sustainability programme. For the piSCES project, there were 2 sites that were chosen. First is called Polar Fish. It's a standalone cold stores, about 30 years old. In terms of the energy consumption, it has an MIC of 190 kVA and would fall into a DG6 category. The other site we chose was here, the main processing site. At this site, we carry out processing, freezing, and there's also more cold storage, but also an ice plant facility. And it was this ice plant facility that was chosen to take part in piSCES. Similar to Polar, Arctic has been established for over 30 years. It's a much larger site, an MIC of 6,000 kVA, and it belongs in the DG7 category. So just on to the Polar site. As I mentioned, this is an off-site location, consists of 2 cold stores, one slightly larger than the other, both of them running off the same refrigeration plant. Historically, we paid no real attention to the time of day or the price of electricity we were paying in order to keep the rooms cold. The rooms ran at a single temperature set point 24/7 with no optimization taken into account. What happened when piSCES became involved in 2018, they were very easily able to integrate within our existing control system, so caused no disruption to the way the plant ran. Fans, coolers, etc. all ran exactly as before. What they were able to do, though, they were able to improve and maintain our system constraints and the alerts. So we have much greater flexibility now in the temperature constraints within the plant. And the way that piSCES works, running an algorithm on an hourly basis, it was able to head off any historic alerts we might get. We found that we were receiving less alerts about temperature rises, as I say, due to piSCES monitoring the refrigeration much more carefully than you could do manually. One of the other benefits we found from working with piSCES in this area, it allowed us to arbitrage with the tariff in the electricity market. So, as others have explained, it means you can boost your energy consumption when the price is cheap, and then you can ramp down your energy consumption when prices are going to be expensive. And that's led to a significant saving on the Polar Fish site. What we also found from working with piSCES is their modelling techniques led to further efficiencies and savings, more of which I'll come to at the end. So within the main site here, as I said, it was the ice plant that was chosen for the piSCES project. This was because it could serve as a standalone project and wouldn't impact on any of the processing, freezing facilities on site. The ice plant obviously is involved in making flake and slush ice that's used for our tankers to bring fish up from the boats at the pier. Historically, much like Polar, not much attention was paid to the ice plant. It was switched on and off manually for an estimated amount of time whenever somebody needed ice for either bins or for one of the trucks. What we found through testing with piSCES initially is we were better able to establish how long it takes for us to make 1 tonne of ice, and that alone has resulted in a saving. The way that piSCES has been working with the ice plant, it accepts a daily ice order remotely and can automatically actuate the plant at the most economic time. So if we decide we want 10 tonnes of ice for 8 o'clock the next morning, rather than us switching on the ice plant perhaps overnight or for the full day the day before and paying no attention to the rates of electricity, what piSCES can do is can plot the most economic times that can make the ice for us. And what we found with that is it gives us, again, greater flexibility in how we run the ice plant. We can set default orders, we can set minimum amounts, and these can be overridden and adjusted very easily remotely. It saves our engineer having to manually attend the ice plant. And what we also find with piSCES here is that it can adjust depending on whether the expected amount of ice was used the day before. It can either increase or decrease automatically the amount of ice that it's looking to make for the following day. So some of the outcomes that we found from working with piSCES, it definitely fits in with our company's sustainability goals and with corporate social responsibility. From using the latest technology, it not only leads to a cost saving for us, but it also leads to a green solution and a green saving for the environment. As mentioned before, there were significant savings that we expect from using piSCES. In Polar, we found that marked against a baseline of what we used to do, piSCES has managed to save 18% on the electricity consumption. And in the ice plant here in Arctic, we find that improves even more to around 29%. Another benefit, as I've mentioned, is with the system piSCES being so flexible, it completely automates a lot of what used to be a manual process and has freed up valuable time, specifically for our chief engineer, who can now spend more time based around the factory and the machinery and not moving back and forth between Polar site, the ice plant and the factory. The constraints and the alerts, as I mentioned, with piSCES have been improved, and this has led to better performance. Again, the algorithm allows for a quicker response to any temperature changes. It means that we're not having to wait for an alert to come through. And also, as mentioned before, we found there was some other efficiencies that we did not foresee. Through the initial testing with piSCES, it really allowed us to focus in on our cold stores. They said they were 30 years old, but we put a lot of effort into ensuring a more consistent temperature in there, which led to more savings. So things like improving the lighting and taking out old lights, putting in LED lights. We improved the door access. We purchased fast-acting roller doors and created an air curtain within inside the cold stores. All this led to reduced losses in cold when doors were open and when lights are on, and we were able to give piSCES a much more consistent temperature to work with. And what we also found was that if we made an adjustment to how we stacked our product in the cold stores, we could improve the airflow, and that was again able to give piSCES a much better platform to work with. Through those initial tests with piSCES and through them implementing their system, we found that on top of all those initiatives, there was less ice building up in cold stores. As a result of that, we were able to adjust our defrost programs. We could spend less energy and less time on defrosts, and that in turn has led to further savings, as seen in the 18% at Polar. Through working with Sean and the team in piSCES, we've also found our knowledge of the electricity markets has improved, and it gives us greater confidence when we're going to renegotiate electricity contracts. We're aware of the different charges, different changes in charges year on year, and it gives us much more confidence going forward. And of course, looking into the future, we see that there's great potential with piSCES and renewable energy on site. It's already set up to cater for solar and wind. Those are the two big renewable energy sources that we ourselves will be looking to implement at least one of those over the next few years, which again, as you've seen at Milford Haven, can only improve your flexibility in when you're using energy, and then leads to a great sharing and a great saving. So that's it from me. I'll pass you back to John. Thank you very much for your time.
So thank you, Sean, who will give an overview of the piSCES platform, slightly more in depth than at the start. And Sean, I'll pass it over to you now.
Thanks, John. Can you see my screen?
Yeah, you're not in presenter mode, that's the only thing.
Yeah, okay. Okay.
Yeah.
Okay, so so what I'll do then, guys, is I'll try and build on the previous presentations and pull it together into how then the platform looks and how it operates. So this is where I finished at the introduction stage. That's basically was just, you know, what is piSCES? So again, just to give maybe a graphic on that, basically the blue line is a typical day, and as I mentioned, the price of energy changes every half an hour. So you have 48 periods in the day where the price of energy is different, and you know that the day ahead. Okay, so this is in euros per megawatt hour. So it was you know, roughly 3 or maybe 3 cents during the night. It went up to about 5 cents then during the day, but then it peaks. It's a price of electricity is all based on supply and demand. It peaks at around 27 cents and then comes back down again. So that every day is different depending on, you know, weather conditions and supply and demand, as I say. A site like Polar and Arctic are on the half hour. So there's basically 48 opportunities every day to optimize that. Other sites like Castletownbere and, as Tam mentioned, Milford Haven are on a tariff. So they're on a night tariff of maybe, you know, 6 cents, a day tariff of around 8 or 9 cents, and then a peak tariff of around 14 cents. So we've sites both on tariffs and on the wholesale rate. And this was a site that we also worked with, and their original load profile is this black line. And basically, so they were using maybe about 80 kilowatts during the night. They went up to around 250 kilowatts during the day, and they peaked at over 300 kilowatts. And as you see, they're actually using more energy when the price is expensive, and they're using very little energy when it's cheap. So with optimization, we would use the same amount of energy during the day, but we would just consume it at different times, and that's why flexibility is so important. So basically, our piSCES system would have ramped up and down that load, that flexible load, such that they were very busy during the night, and during the day. Then obviously we were just maintaining and as little as possible. And again, we would ramp up when the price went down again. So there's significant savings as we've seen for that. So to do that, you have to model the profile of the flexible load that you want to manipulate. And in this case, this is just a screenshot of the coal stores in Polar, as Philip was explaining. And a lot going on here, and these are basically the compressors coming on and off at the bottom here. The orange line is the amount of energy that's being used. And basically, we did a lot of work to model how the rooms react when you increase temperature and when you let it slide back. Okay, so we set the minimum temperatures at minus 18 and more recently at minus 19 degrees C, and we also go up to minus 25 degrees C. So we integrated directly with the refrigeration control system, and we put a lot of monitoring equipment into the rooms to make sure the temperature spread was good and we weren't getting any warm spots, and we averaged those temperatures in the rooms to give us the temperature. Okay, so by doing lots and lots of trials of ramping up and ramping that down, we were able to build a prediction model of how that room reacts. And obviously there was other factors like ambient temperature and how full the rooms were, and the amount of traffic going in and out of them. So we had to have different thermal profiles and prediction models for all the different criteria. So this is what the piSCES system looks like. Okay, basically on the left-hand side here, you've got these all expand out into our modules. So you have, a weather module, we have a load module, we have an electricity markets module, and a solar module, and we have a settings module here where you set up all of the criteria for your site, be it what kind of solar is there, what market tariffs you're on, all of that criteria. And basically, there's a lot going on in this top graph, but basically, if you just follow the blue line, this is the price of energy on the half hour. Okay, so this was on a particular day in polar. So obviously, it was around 5-6 cents during the night, and it goes up to 22 or 3 cents during the day. So obviously, the piSCES system is looking at this 24 hours ahead. Okay. So we try to put everything on this front page so that Philip and Hugh, the chief engineer, can see at a glance exactly what's happening, and they can toggle to look at yesterday, and they can also look ahead to see what tomorrow is going to look like. The bottom graph here, you see we have 3 temperature set points. So previously, as I said, the cold rooms were being run at a single temperature. It was always trying to hunt around minus 23 degrees. Okay, and it didn't pay any attention to the price of energy at that time. So what we did is we have 3 set points now. You can set it to minus 25, minus 22 in the middle, or you can actually switch it off. And when we switch it off, we still keep the fans and everything running to make sure there's good airflow around the product. Okay, and we predict. Then the prediction model then predicts what that temperature is going to be every hour, and it reruns the algorithm every hour to make sure it's staying in line. So the blue line is the actual temperature. So we ran this screenshot at 2 o'clock on a particular day, and the purple line is the predicted. So obviously, when it's off here, you see the temperature gradually rises, and that profile is what came out of our prediction models. Okay, you see here at 3 a.m. between 2 and 3 a.m. We have this defrost cycle. Defrosting, as Philip explained, was obviously on coolers you get ice build up, and they have to be defrosted periodically. Before piSCES got involved with Polar, they were doing 2 defrosts every day, and a defrost is a double whammy. They've got heater coils in the coolers that they heat up to melt off any ice that builds up on the coolers. So obviously that's costing you energy to use those heaters, and also it's introducing heat into the room that you don't want. Okay, so because of the better performance of the rooms due to piSCES and therefore being less ice buildup, we were able to find that we could go. We did tests with the guys there, and we successfully worked that we can do just 1 defrost a day, and we also chose 2 to 3 a.m. As the time to do it, because that's always the cheapest time. Prices are always cheaper at night. Before, they were actually doing it at 7 a.m. and 7 p.m., which are much more expensive. So we were able to time that. So that's what Philip meant by defrost optimization. So the algorithm worked out that while the price was cheap, between midnight and 8 a.m., that it would work very hard. We want to work hard across that period because the price is cheap. Okay, and it every hour predicts what the temperature is going to be in the next hour, 24 hours ahead. Obviously, then as the price starts to rise here at 8 a.m., we're going to switch off, and we switched off from 8 a.m. to 4 p.m., which at the beginning we didn't think we'd be able to switch off for that long. But obviously, by doing extra work at night, we were able to buy that energy back. So we're using no energy at that time. Okay, so the predicted cost then obviously comes way down. Obviously, there's still fans and stuff running, but your predicted cost comes way down. Obviously, as the temperature then starts to rise, this screenshot, as I said, was taken at 2 o'clock. We are predicting at 4 o'clock we're going to have to switch on again to minus 25. So we're going to make it cold again. So it's going to get cold again, and this is our profile as what it's going to do. And again, at 7 p.m., then we can switch off again to miss this other small peak. So the algorithm works out over a 24-hour period ahead what to do, and keeps the cold store within certain constraints. like temperature. And also, if we have other alerts and mechanisms built in, fail safes, where if the gap between the predicted and the actual is of a certain size, we may turn on the cold store regardless. So obviously, if somebody left a door open, really what that means is that the cold store is not operating to the way it should be, to its profile. So therefore, there's an issue, and if it continues, obviously, then alerts are sent out, and if manual intervention is required. So that's basically a cold store. So cold store is a very good example of flexible load. So basically, we're ramping it up and ramping it down. This is the front page of the Arctic site, also in Killybegs, where we make ice. And basically, as Philip mentioned, historically they would just manually switch on and then kind of keep an eye on it, and when they had the required amount of ice, they'd go and switch it off. So there was quite a lot of manual intervention required. What we've done with piSCES, again, we've interacted with the ice control system, and we're obviously going to turn it on and turn it off to suit at the cheapest time. So basically there's a default ice order. So depending on how busy the guys are, they can set that order to, and here it's set to 5 tons. We've also set a minimum level in the ice hoppers. If the guys decide we need 5 ton for 8 o'clock tomorrow morning, the system works out when to make that ice. So obviously, again, the blue line, it was roughly around 6 cents during the night, and it goes up to 19 cents or so during the day. So it works out. It knows how long it takes to make a ton of ice, and it works out what's the most economic time before 8 a.m. tomorrow to do that. So this, obviously, it would have made ice between midnight and 8 a.m. It would have switched off all day to miss the high prices, and it would come on again at 8 p.m. and finish off the ice order before midnight. And obviously, then you can go into tomorrow and look at what's happening there. Okay, so again, it does it at the most economic time. Building on what Tam mentioned, similar type of system for their ice plant. Was much more complicated for us because there was no control system for it. It was a completely manual, so we had to put in a smart relay that the piSCES system could talk directly to. So again, the operators can put in an ice request for 8 a.m. tomorrow morning, and it will make it at the most opportune time. As you see in Milford Haven, they're not on the half hourly; they're on a night rate and a day rate. And also in Milford Haven, we have solar on the roof. So our solar prediction model predicts how much solar we're going to have in the coming period based on weather forecasting and a lot of other items. And so we're trying to maximize using the solar. Previously, as Tam mentioned, that solar was being spilled onto the grid, and so it's almost free energy to them. So basically, you optimize that. So again, the ice machines turn on and off to make the required amount of ice for the required time at the cheapest to avail of market prices and solar energy. Okay. So just a quick graphic to bring that together. Again, this is the graph that I showed you earlier, where you would have optimized your load here. But obviously, when you introduce renewable energy, a site may have some amount of wind and also a lot of solar. You want to be able to maximize that there, and then therefore what you buy from the grid is in this blue line. So obviously at night you've only just got some wind, so you're buying most of your energy at the cheapest price. And then obviously as your solar and everything kicks in during the day, you're using much less energy because you're buying much less energy from the grid because you're using your own solar, and also you've ramped it down from the optimization side. And as you see here, it actually then goes negative. Between maybe 3 o'clock and 8 o'clock, it goes negative. But it's going negative at that, which means it's actually spilling energy out onto the grid. And it does it at a time when the price is highest. So you're buying energy cheaply here at maybe 3 or 4 cents, and then you potentially could be selling it at the 27 cents. So that's the whole idea. That's the arbitrage we speak about. Okay. So just to pull all this together and linking it to the objectives we had at the beginning of the project, really, I suppose the piSCES platform is a prediction and optimization system, leveraging the flexibility in thermal loads such as ice plants and cold storage. and to avail of those time of use tariffs and integrating renewable energy on site. As mentioned by both Philip and Tam, the significant savings in Polar and Arctic ice, and even higher again in Packaway because of the solar issue there, and using that spill, they can save significant amounts of money. Another major achievement for the project was the smart energy cluster system that was delivered in Milford Haven. This really is the future. This can be, as I say, a central pillar of the clean energy transition, enabling consumers to share energy amongst themselves will incentivize them to integrate renewable energy, and that's really what we want to do with piSCES. There's kind of barriers in the way of energy sharing, which we were able to overcome in the UK. The laws in Ireland are slightly different, and in most of Europe, and the EU have recently issued directives through the Renewable Energy Directive and the Electricity Market Directive, which will force governments to bring in legislation to allow peer-to-peer sharing and to give some kind of an incentivization to allow people to do that. So if you can picture exactly what Tam was explaining, you can build these energy clusters, and with our technology, potentially with the optimization and prediction, you can design a renewable energy system to suit a cluster. So if you've got 20 or 50 or hundreds of different companies, you can actually have a renewable energy system designed to suit it and let that energy park be sustainable. Okay, so that's where we see the future. We've obviously found that, you know, cooperate us as research and development institutions, cooperating with industry like Atlantic Dawn and the Port of Milford Haven and Williams and these guys. It's given lots of other added benefits. It's stuff that's we didn't foresee at the beginning of the project. Have come up, and obviously sites like we're also doing reports for Castleton Co-op as well, as Martina said. So, you know, the opportunities are limitless, really. Obviously, we mentioned that the platform, because it's completely automated, it frees up people, and it gives that, you know, gives other added benefits like the alerts and the constraints that we can build into the automatic system. And it's obviously linking in with what Martina said with the Origin Green program. You know, all companies have sustainability goals and corporate social responsibility targets. So this is a central tenet of it. Okay, and obviously, you know, you've got a product like frozen fish is worth a lot of money, and obviously, if you can improve the product, the safety of it, and the site performance, it brings that competitiveness and makes these sites more sustainable. So that very quickly, guys, is what the piSCES project did, has done, and is still doing, and how we've delivered with our partners. So I think the Q&A session is next, John. Is that correct?
That's right, Sean. Yeah. So we got a question in from Gianluca Lepari regarding energy clusters, smart energy clusters. Did you encounter any barriers or limitations posed by the regulations or the system operators to the creation and management of the energy clusters, especially regarding local trading? I know you touched on that in your presentation, Sean, but Tam answered it in line. But have you any other perspectives on the Irish situation in particular?
Yeah. So yeah, as I mentioned in my talk, the mechanisms of how the electricity markets work in the UK are different to Ireland. So we were able to do, obviously Tam mentioned we worked with Energy Local and how the project in Bethesda works. So the barriers in the UK are a lot less. You're allowed to within, you might be able to add to this, Tam, but you know, behind a substation, the ability, you're still using the distribution grid, so there are some distribution charges you have to pay, but you don't have to pay the other transmission charges and other PSO levies and stuff like that. From an Irish perspective, you're not allowed to do that. If I share with my next door neighbour, but I get very little for spilling that energy, and my next door neighbour pays for the energy as if it was as if it came from a generating station hundreds of miles away. So on the legislation piece, then those barriers are envisaged that they will be relaxed. We're still a little unsure. The EU directives are being transposed early. The first one, the renewable energy directive, is to be transposed in Ireland in January, and the electricity market directive is in June. So we are working with the regulator, the energy regulator here, as to exactly how that might happen in Ireland, and also keeping a very close eye on what's happening around Europe. So the peer-to-peer energy sharing will be allowed, but unless there's some financial reason for doing it, so we were not sure whether some of the charges may be relaxed or there might be some support scheme for it. We're not sure. So hope that answers the question. You might be able to add something to that, Tam, from a UK side.
I would just reiterate what I put in my comment, is that it's not that it's either allowed or disallowed at the moment in the UK. It's more that the regulators are still to take a view. I know that it's on the radar, and we expect positive affirmation from them that clustering on the low voltage side of the network would be something that can be approved, because essentially what you're doing is balancing the local grid. When people are creating these sorts of sites where the businesses or the consumers are geographically removed from each other and are on different substations, that's when it becomes more complicated. And I think it's more difficult to legitimise that, because you're not actually balancing in the grid in that respect. So it's all about keeping this local generation and local consumption on the low voltage side of the network.
Does that answer the question, John, do you think?
I think so, yeah. Hopefully, Gianluca, that gives you a bit of insight. Does anybody else have any questions? I suppose one question is, obviously we're concentrating on fish processors here primarily, Sean. Can you see any other sectors where this would be, this piSCES system would be of benefit?
Yeah, I mean, anyone really with flexible loads is a potential client for this technology. Fish processing is a very good example in that there's a lot of thermal loads, like I explained in my presentation, between ice making and cold storage. But other food processing would also have, a lot of thermal loads. So basically, cold storage, ice making can be in lots of different areas. And as I said, if the peer-to-peer energy sharing aspect becomes a reality, it would allow consumers to become what's known as prosumers. They're people that are actually not just buying energy, but they're involved in the energy market. And obviously, to be involved in the market, you have to have some some system or some intelligence, and that's what piSCES gives you. It gives you the intelligence and the control to actually be part of the market. So as you see with the likes of Polar and Arctic and Milford Haven, they're actually trading in the market now, because they're using energy when it's cheapest and when using as little as possible when it's expensive, and also maximizing and optimizing any renewable energy that they have on site.
Okay, thanks, Sean. Samantha Richardson actually asked the exact same question, just as I asked it to you, Sean. So hopefully, Samantha, that's answered your question as well. Does anybody else have any questions? Oh, hang on, we have anything? No, we don't. I have a question from this anonymous. When the project ends, will the piSCES platform be made available to other organisations outside the ports that have been test sites?
Yeah, potentially. I mean, obviously, from a WIT point of view, we have a technology transfer department which looks at how this technology could be used in other areas. So certainly it's not going to be just left on a shelf. There's a lot. It's obviously a huge amount of effort has gone into pulling it together and to making it as accurate and as usable as it is. So yeah, it would be foreseen that it would be used in other areas and also potentially rolled out to other sites. So if anybody has any questions on that, just contact me directly. My email address is slyons@tssg.org. I might just put that in the chat box there, just as we're talking.
Cool. So a couple of follow-up questions from Samantha. So are there plans to develop piSCES 2.0, and how and where would the team like to see piSCES progress?
Well, exactly. Again, I think following on to what I just said, as the clean energy transition develops and energy laws are changed to allow that to happen, as I said, you need to have a system which allows you to integrate with the market. So the clustering element that we've begun in Milford Haven has huge possibilities. And really, we're, as I say, keeping a very close eye as to how these EU directives will be transposed, not only in Ireland but across Europe, because we see, potentially, piSCES as you saw today is very much a behind the meter technology. It's optimizing just a single factory at a time or a single site at a time. Whereas if peer-to-peer sharing becomes a reality, it could also play a role beyond the meter or the other side of the meter in energy clusters.
Okay, thanks for that, Sean. I think that's all the questions we have for now. So first of all, thanks to everybody again for attending today. It was great to have so many people online, so close to Christmas. Thanks to all the presenters for taking the time and for being great partners to work with over the past few years. Hopefully we'll have the opportunity to continue and to work again together in future. So that's all from me. I don't know if you have any closing remarks, Sean?
Just before you sign off, John, I'd just like to a couple of thanks. I'd like to obviously that we have 4 partners in this project: Port of Milford Haven, Bord Iascaigh and Cardiff University, and I'd like to thank them all for their massive effort over the three and a half years or so that the project ran. I think it was a great working relationship and worked very well. Particularly like to thank my own team in TSSG. The amount of work that was done was fabulous, and I think you can see it in the results. And I'd also like to thank the Ireland Wales programme themselves. It was a great system, and in particular, I'd like to thank Samantha Richardson, who was our development officer, who was a fantastic help and was always at hand to help out. So thanks to everyone that was involved, and thanks to everybody today for attending. And I hope you enjoyed it and got something from it.